Galaxies spin at impossible speeds without flying apart. This simple fact hides a cosmic secret, an invisible substance called dark matter that holds the universe together. By the end of this journey, you will understand the fundamental force that sculpts our cosmos and dictates its ultimate fate. We will uncover why stars on the edge of galaxies defy gravity and what strange, unseen particles could be saturating the space around you. How much of reality do you think remains hidden from our view a galaxy should tear itself to pieces? Think of a carousel spinning so fast that anyone standing near the edge would be flung far out into the night. Yet when astronomers like Vera Rubin trained their telescopes on distant galaxies, they saw something impossible. Stars far from the galactic center, out in the lonely spiral arms, were whipping around at nearly the same incredible speed as those nestled close to the heart. This was not just a small error in calculation. It was a fundamental break from the laws of gravity as we understood them. The gravitational glue of all the visible stars, gas, and dust was simply not enough to hold these speeding stars in their orbits. The galaxy should have been a cosmic explosion of scattered stars, a beautiful but fleeting firework. Instead, it held together, a silent testament to a force we could not see. This mystery was first glimpsed decades earlier by a scientist named Zwicky. Studying the frantic motion of galaxies within a vast cluster, he realized their visible mass was a pitiful fraction of what was needed to keep the cluster gravitationally bound. He called this missing mass dunkel materie, dark matter, a ghostly presence that offered no light, only the undeniable pull of its gravity. The evidence mounted, not from what we could see in the cosmos, but from what we could not. It was like watching a spinning top that never wobbled or fell, guided by an invisible hand. The data plots were unequivocal, showing a flat rotation curve where physics predicted a steep decline. This was the moment astronomy was turned inside out. We had been studying the universe by the light it gave, like trying to understand a city by only looking at its streetlights. But what about the unseen streets, the dark buildings, the entire infrastructure hidden in the shadows? The luminous stars we adore are merely the glittering decoration on the surface of a much deeper, much darker ocean. What else is holding this cosmic city together right now, all around us? The evidence for this invisible heavyweight was not confined to the spinning of individual galaxies. To find the next clue, we must look at the grandest structures in the universe, colossal gatherings of thousands of galaxies bound together by gravity. Imagine trying to weigh such a cluster, not with a scale, but by watching how its immense gravity warps the very fabric of space around it. This is the phenomenon of gravitational lensing. Just as a magnifying glass bends light to distort the view of an object behind it, the gravitational pull of a massive galaxy cluster acts as a cosmic lens. It twists and stretches the light from even more distant galaxies, creating bizarre, shimmering arcs and multiple mirage-like images in the sky. When astronomers calculated how much visible mass all the stars and glowing gas in the cluster should be causing this distortion, the numbers did not add up. The gravitational pull was hundreds of times stronger than the visible material could possibly produce. The cosmic seesaw was wildly unbalanced, with an unseen heavyweight pushing down with incredible force. This was the missing mass problem starkly revealed. The most compelling evidence for this dark, dominant component comes from cosmic collisions. Consider the Bullet Cluster, a spectacular crash of two galaxy clusters. In this violent event, the clouds of hot gas, which make up most of the normal, visible matter, slammed into each other and slowed down. but the dark matter, which does not interact with itself or normal matter in any way except through gravity, sailed right through the collision. By mapping the mass using gravitational lensing, astronomers could see where the true weight of the clusters resided. The result was breathtaking. The dark matter had become separated from the normal matter, leaving a ghostly silhouette of mass where there was almost no light. It was a direct observation of the invisible, a cosmic fingerprint proving that most of what holds the universe together is a substance we cannot see, touch, or shine a light upon. This forces a profound reflection. We have been mapping the cosmos by its light, but the true architecture, the hidden framework of reality, has been built from something else entirely. What could this mysterious substance possibly be made of? The expected drop in speed never happens. Out in the galactic suburbs, stars race along at nearly the same blistering pace as their neighbors closer to the bright city center. This creates a flat line on a graph, a rotation curve that stubbornly refuses to fall, defying the fundamental rules of gravity. It is as if every car on a vast cosmic highway, regardless of whether it is near the downtown exit or far out in the rural stretches, maintained the exact same high speed. This simple, flat line is one of the most powerful pieces of evidence for our invisible cosmic companion. In the 1970s, astronomer Vera Rubin and her colleagues transformed this puzzling observation into undeniable proof. Their meticulous studies of spiral galaxies, including our neighbor Andromeda, showed this flat curve was not an exception. It was the rule. The gravitational pull needed to keep these outer stars from flying off into the void had to be coming from somewhere. The answer was a massive, unseen halo of dark matter, a vast spherical cloud enveloping the entire galaxy, extending far beyond its last visible star. Astrophysicist Priyambada Natarajan explains that this very flatness is the telltale signature of how dark matter is arranged, its gravitational influence shaping the galaxy from the outside in. When scientists try to build a galaxy inside a computer using only the ordinary matter we see, the simulation fails. The resulting galactic disk is a messy, unstable wreck. But when they add the precise distribution of dark matter suggested by those flat rotation curves, the virtual galaxy settles down, spinning gracefully, its spiral arms perfectly defined. This unseen scaffold provides the stable gravitational foundation that allows luminous galaxies like our own Milky Way to form and endure. Without this cosmic glue, the orderly rotation of our galaxy would descend into chaos, with stars scattering into the emptiness between galaxies. So while the rules of motion on our earthly highways are well understood, the galaxy itself hints at a hidden rulebook written in the language of an invisible force. This profound anomaly pushes us to ask the next inevitable question. What is this mysterious substance, and how can something so pervasive remain so completely hidden from our view? The universe holds a fossilized imprint of its own birth, a faint glow that fills every corner of the sky. This is the cosmic microwave background, the cooled remnant of the Big Bang's first light. To our eyes, it appears as uniform static, but to sensitive instruments like the Planck and WMAP satellites, it reveals a breathtakingly detailed blueprint. Etched into this ancient afterglow are tiny variations in temperature, minuscule ripples that are the seeds of everything we see today. These ripples are the gravitational footprints of dark matter, the crucial ingredient that allowed the universe to build galaxies, clusters, and the vast cosmic web. Without this invisible scaffolding, those primordial fluctuations would have been too weak to ever collapse into the grand structures we observe. The pattern is so clear that we can read the recipe for the cosmos directly from this data. Ordinary matter, the stuff of stars and planets, makes up a mere 5% of the universe's total content. Dark matter, by contrast, accounts for 27%, a dominant, unseen force that provided the gravitational anchors for the future. This influence is captured in effects like the Sachs-Wolf effect, where the gravity of dark matter concentrations subtly red shifts or blue shifts the ancient light as it travels across the cosmos, leaving a permanent mark. Nobel laureate John Mather clarifies that without dark matter's gravitational pull, the universe would be a much smoother, emptier place, devoid of the great galaxy clusters and the sprawling filaments of matter that connect them. The cosmic microwave background is therefore our most powerful evidence that the universe's visible architecture was drawn by an invisible hand. These subtle ripples in space-time are the traces of a hidden architect whose work began in the first moments of time and set the stage for everything that followed. If dark matter is this fundamental to the very structure of reality, what could it possibly be made of, and why has it remained so elusive to our every attempt at detection? This cosmic blueprint leads us to a powerful tool for mapping the invisible. Picture the fabric of space as a vast, flexible sheet. When an unseen concentration of dark matter rests upon it, the sheet warps, bending the path of light from any object traveling behind it. This is gravitational lensing, a cosmic funhouse mirror that distorts our view of the distant universe. We see this as multiple, shimmering images of a single quasar, or as long, stretched arcs of light from faraway galaxies curved around a foreground cluster. These are not optical illusions, but direct gravitational footprints. Astronomers like Dr. Dan Coe use these cosmic mirages as natural telescopes, magnifying the faintest, most distant objects and, in the process, quantifying the very clumpiness of dark matter itself. The Hubble Space Telescope's deep-field images are filled with these subtle distortions, a gallery of bent light that reveals the hidden architecture of the cosmos. The mechanics of this phenomenon are as elegant as they are revealing. In a perfect alignment, we witness an Einstein ring, a complete circle of light formed when a distant galaxy is perfectly framed by an intervening mass of dark matter. More often, we see weak lensing, a slight shearing effect where the shapes of thousands of background galaxies are stretched in a coherent direction, like blades of grass bent by an unseen wind. Sophisticated algorithms analyze this sea of distorted shapes, painstakingly reconstructing a three-dimensional map of the invisible mass responsible for the warping. The galaxy cluster Abell 1689 serves as a stunning example. Its core is a dense knot of dark matter, revealed not by any light it emits, but by the intricate spider web of bent light that traces its immense gravitational field. This mapping technique confirms that dark matter is not a smooth, uniform fog, but a clumpy, hierarchical scaffolding upon which galaxies are built. How often do we understand the hidden world through its indirect effects, much like a detective piecing together a scene from fingerprints and stray clues? We cannot touch dark matter, but we can watch it push and pull on the one thing we can see, light itself. These detailed maps do more than just confirm its presence. They begin to tell us how it behaves, how it clusters under its own gravity, and how it has shaped the universe over billions of years. This intricate cosmic cartography points us toward the next great mystery, forcing us to ask what kind of particle, what fundamental ingredient of reality, could possibly possess such profound gravity while remaining so utterly, completely transparent to our every attempt at a direct glance. This cosmic web is the largest structure we can possibly comprehend, a network of ghostly filaments spanning billions of light years. If you could see the universe with dark matter vision, you would not see scattered islands of galaxies, but a single, interconnected tapestry, with brilliant clusters glowing at the intersections of invisible threads. This is the grand architecture forged by dark matter. The luminous galaxies we chart are merely the glittering ornaments hanging from this hidden framework. Cosmologist Carlos Frenk explains that dark matter had to be cold and slow-moving from the beginning. This crucial quality allowed it to clump together first, forming vast gravitational wells into which ordinary matter could later flow, cooling and condensing to ignite the first stars. Without this pre-existing scaffold, the force of the primordial expansion would have ripped apart any incipient structures, leaving the universe a formless, diffuse haze. We can watch this cosmic drama unfold inside supercomputers. Simulations like the Millennium Run begin with the tiny ripples observed in the cosmic microwave background, and then let the laws of physics play out over billions of virtual years. The result is always the same, an intricate cosmic web that matches the large-scale galaxy surveys with stunning accuracy, but only when dark matter forms the foundational skeleton. This hidden infrastructure dictates everything we see, from the great walls and voids to the graceful mergers of galaxies. Our own galactic home, the Laniakea supercluster, is a testament to this. We are not simply located in a random part of space, we are flowing. The Milky Way, along with millions of other galaxies, is being pulled by the gravitational currents of an immense, unseen concentration of dark matter known as the Great Attractor. Our entire local universe is on a slow, cosmic river journey toward this hidden gravitational heart. The profound irony is inescapable. The most massive components of the cosmos, the great walls and filaments of the cosmic web, are entirely invisible. They are the negative space that gives the positive its form, the unseen continents that define the ocean of our reality. We have mapped the shorelines of the visible universe, but we are only now beginning to understand the tides of an unseen sea. This grand, invisible architecture forces a final, pressing question. If dark matter is everywhere, shaping everything, how do we ever hope to touch it, to prove its existence beyond the shadow of a doubt, and finally identify what it truly is? The prevailing map for this unseen cosmos is known as the Lambda CDM model, a framework that has become the standard model of cosmology. This name might sound technical, but its components are the fundamental forces shaping our universe. Lambda represents dark energy, the mysterious force driving the cosmic acceleration. CDM stands for cold dark matter, the slow-moving, gravitational anchor for all structure. Within this model, ordinary matter, the stuff of stars and planets and of us, is almost a secondary detail, filling in the luminous gaps of a scaffold built by something else. The cold nature of this dark matter is crucial. Imagine two different kinds of cosmic fog. A hot, fast-moving fog would stream freely, smoothing out the universe and preventing small structures from ever forming. But a cold, sluggish fog moves slowly enough that its own gravity can draw it into clumps. These clumps act as gravitational seeds, pulling in more matter over billions of years to eventually form the galaxies we see. This is precisely what the model predicts and what our most powerful supercomputer simulations confirm, when physicists like Dr. Michael Turner run the numbers, starting with the initial conditions from the cosmic microwave background. The cold dark matter model successfully grows a universe that looks remarkably like our own, complete with a cosmic web and galaxy distribution that matches our deepest sky surveys. It even explains more puzzling observations, such as why tiny dwarf galaxies seem to be so overwhelmingly dominated by dark matter. Cold dark matter piles up intensely in these small, early halos, creating incredibly dense gravitational anchors. Yet, like any good map, the model also highlights areas where the terrain does not quite match the chart. Some of the smallest galaxies appear less numerous than the simulations predict, and their dark matter cores seem less dense than expected. These are not failures of the model, but rather its greatest strength, pointing scientists toward new physics and a more nuanced understanding of how dark matter interacts with the normal universe. A scientific model is not a final answer, but a guide for exploration, a tool that is refined with every new observation. This incredibly successful framework gives us our best picture of the cosmic architecture, but it raises a profound and tangible question. If cold dark matter is real, what exactly is the particle that constitutes it? But what if dark matter is not entirely cold and sluggish? A second compelling theory suggests it could be warm, possessing slightly more energy, and moving at a significant fraction of light speed. This subtle shift in character could solve some of the most persistent puzzles in our cosmic maps. While cold dark matter clumps readily into tiny, dense halos, warm dark matter particles would stream freely through space, their velocity preventing them from settling into the very smallest structures. This free streaming effect acts like a cosmic filter, smoothing out the smallest clumps and potentially explaining why we observe fewer tiny dwarf galaxies orbiting our Milky Way than the simplest cold dark matter simulations predict. This is known as the missing satellites problem. A universe with warm dark matter would still build the immense filaments and grand clusters of the cosmic web, but it might lack the tiniest, darkest building blocks. Physicist Alexei Boyarsky points out that a candidate like the sterile neutrino, a hypothetical, heavier cousin to the known neutrinos, could perfectly fit this warm dark matter role. Its slight warmth would suppress the formation of numerous small halos, bringing our theoretical predictions into closer alignment with the observed galactic population. We can even look for evidence in the light from distant quasars. As this light travels through the cosmos, it passes through clouds of intergalactic hydrogen, which absorb specific wavelengths and create a forest of absorption lines in the quasar's spectrum. The detailed structure of this Lyman alpha forest is exquisitely sensitive to the small-scale clumpiness of dark matter. Current data places tight constraints, suggesting that if dark matter is warm, its particles must still be relatively heavy, limiting just how far they can stream. Consider the Draco Dwarf Galaxy, a small, faint satellite of the Milky Way. Some studies suggest its inner dark matter profile might be less densely cored than cold dark matter predicts, a feature that could be more naturally explained if the dark matter particles had enough energy to resist collapsing into an extremely dense center. This invites a deeper reflection on the nature of scientific theories. Is the simplest, coldest model the complete picture, or does the universe demand a slightly more complex, warmer alternative to account for all the clues? Our search for dark matter's true identity is a process of refinement, where every astronomical anomaly forces us to reconsider the fundamental properties of the invisible majority. This ongoing debate between cold and warm scenarios naturally pushes us toward the next frontier, the direct hunt for the particle itself. Yet a third possibility challenges the very foundations of physics. What if our understanding of gravity itself is incomplete? This is the radical proposition of modified Newtonian dynamics, or MOND. Instead of filling the cosmos with an invisible substance, physicist Mordechai Milgrom suggested that gravity simply behaves differently at the extremely faint accelerations found in the outer reaches of galaxies. His hypothesis introduces a critical threshold, a point where the gravitational force stops weakening with distance and instead follows a new rule, strengthening just enough to hold those fast-moving outer stars in place. This single, elegant adjustment can perfectly reproduce the flat rotation curves of countless galaxies without a single gram of dark matter. It is a compelling idea, solving the mystery by rewriting the rulebook rather than inventing a new cosmic ingredient. Scientists like Dr. Stacy McGaw point to the stunningly tight correlation known as the radial acceleration relation. When you plot the observed acceleration of stars in a galaxy against the acceleration predicted by the visible mass alone, the data points from thousands of galaxies fall onto a single, smooth curve. MOND predicted this precise relationship decades before it was observationally confirmed, a triumph of empirical foresight. For its supporters, this is evidence that we are witnessing a fundamental law of nature, not the effect of a hidden particle. However, this elegant solution faces profound challenges on larger cosmic stages. The same gravitational lensing observed in massive galaxy clusters, where light is bent by immense unseen mass, becomes a serious problem for MOND. The theory, in its original form, simply cannot account for the sheer amount of warping we measure. To address this, relativistic extensions like TVS have been developed, weaving modifications of gravity into the fabric of Einstein's theory of relativity. But even these more complex frameworks struggle to explain the detailed blueprint of the cosmic microwave background, which strongly supports the presence of a dark matter component that dominated the early universe. The bullet cluster presents perhaps the most visually stark evidence against a simple modification of gravity. Remember, the dark matter and the normal matter were physically separated during that colossal collision. MOND would still require some form of unseen mass in that specific location to explain the gravitational lensing map, undermining its core premise of doing away with dark matter entirely. The debate is a philosophical chasm at the heart of modern cosmology. Is it more scientifically elegant to modify our fundamental laws of physics, or to accept that the universe is predominantly made of a substance that has so far evaded all our attempts to see it? This tension is not a weakness but a sign of a healthy, thriving scientific process where competing ideas are rigorously tested against the harsh judge of observational data. As we move from the cosmic scale to the particle realm, we carry this question with us, a reminder that the universe often guards its deepest secrets not in the answers we find, but in the questions we are bold enough to ask. One of the most promising candidates for this invisible substance is a hypothetical particle known as a WIMP. WIMP stands for Weakly Interacting Massive Particle, a name that perfectly captures its elusive nature. These particles would be far heavier than a proton, yet they would barely interact with the normal matter that makes up our world. A WIMP could pass through the entire Earth, even through your own body, as if it were not even there, feeling only the faintest tug of gravity. Yet, in the early universe, trillions upon trillions of these particles would have been forged, and their collective gravitational pull is what we now observe holding galaxies together. The beauty of the WIMP hypothesis is its elegant connection to other mysteries in physics. It emerges naturally from theories like supersymmetry, which seek to unite the fundamental forces of nature. Physicist Dr. Elena April, who leads the Xenon Dark Matter Project, notes that WIMP are so compelling because they solve two problems at once. Their predicted thermal relic abundance, a number calculated from their early universe interactions, matches the amount of dark matter we observe almost perfectly. This is often called the WIMP miracle, a tantalizing hint that we might be on the right track. To find them, scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays by a mountain of rock. Experiments like LUX and Panda X use massive vats of ultra-pure liquid xenon, waiting for the telltale flash of light and charge that would signal a WIMP bumping into the nucleus of a xenon atom. This event, a nuclear recoil, would be incredibly rare, requiring years of patient observation. One of the most enduring puzzles in this search comes from the Doma/Libra experiment in Italy. For over 2 decades, its detectors have recorded a faint, rhythmic signal that rises and falls with the seasons. just as a WIMP signal should as Earth moves through the galaxy's dark matter halo. Yet, no other experiment has been able to confirm this finding, creating a long-standing controversy that pushes teams to build ever more sensitive detectors. This painstaking work is a testament to human ingenuity, a hunt for a ghost that requires us to listen for a whisper in a cosmic hurricane. The search for WIMP has driven incredible technological advances, from creating the purest materials on Earth to developing new ways to shield against the faintest background radiation. It is a search that tests not just our instruments, but our very imagination, forcing us to conceive of ways to detect a substance that defines itself by its absence. As these experiments continue to narrow the possibilities for WIMP, the scientific community is broadening its search, considering a whole zoo of other potential particles that could make up the cosmic missing mass. Another compelling candidate emerges not from the realm of heavy particles, but from the ethereal domain of quantum waves. Axions are hypothetical particles so incredibly lightweight that trillions of them could pass through your hand every second without a trace. Theorized by physicists Roberto Pexi and Helen Quinn, the axion was originally proposed to solve a deep puzzle in nuclear physics known as the strong CP problem, a question of why the fundamental forces treat matter and antimatter with such perfect symmetry. The elegant solution they found had a remarkable side effect. It also produced a perfect candidate for dark matter. These particles would be billions of times lighter than electrons, and their behavior would be less like discrete bullets and more like a vast, coherent ocean wave washing through the cosmos. Dr. Leslie Rosenberg describes axions as cosmic waves that could permeate all of space, a single, shimmering field whose collective gravitational influence holds galaxies together. This wave-like nature offers a potential solution to some of the fine-scale problems that challenge the WIMP hypothesis. Because axions are so light and cold, they would not clump into the tiniest, densest halos, potentially explaining why we observe fewer small satellite galaxies than some simulations predict. In fact, a dense cloud of axions could form what is known as a Bose-Einstein condensate, a single quantum state stretching across an entire galaxy. This could manifest as a solitonic core, a smooth, dense ball of dark matter at the center of a dwarf galaxy that aligns with certain astronomical observations better than the sharp cusps predicted by some cold dark matter models. To detect such a ghostly substance, scientists have built extraordinary instruments like the Axion Dark Matter Experiment, or a DMX. It uses a powerful magnetic field inside a resonant cavity, a kind of tuning box, to coax a passing axion to convert into a faint microwave photon. It is like trying to hear a single, specific note played by a single violin in a symphony orchestra of cosmic static. The production mechanism for axions is as strange as their detection. In the hot early universe, the axion field is thought to have been misaligned, like a ball resting on a slope. As the universe expanded and cooled, this ball began to oscillate, and those cosmic oscillations, frozen into the fabric of reality, are what we now perceive as the vast sea of axion dark matter. There is a profound beauty in this idea, where a solution to one of particle physics's most obscure problems might simultaneously unveil the nature of the universe's dominant matter. It reminds us that the cosmos often hides its deepest connections in the most unexpected places. The hunt for the axion opens a divergent path from the WIMP, a road that leads us to consider a universe woven from invisible, wave-like threads. A third possibility drifts even further from the world of familiar particles. Imagine a ghost with a shadow, a sterile neutrino that is the heavier, right-handed counterpart to the standard neutrinos we know. This hypothetical particle would feel only the feeble tug of gravity, completely ignoring the weak nuclear force that governs its lighter cousins. Its existence is a compelling fix for puzzling gaps in our theories, particularly in the data from neutrino oscillation experiments that suggest our current model is incomplete. A sterile neutrino would interact with the known universe only through a faint quantum mechanical mixing with ordinary neutrinos, a whisper of a connection across the particle divide. This subtle link could allow it to decay over cosmic timescales, and in that decay, it might emit a telltale signature, a faint spike of X-ray light at a very specific energy. Astronomers have indeed detected a puzzling, unexplained X-ray line at 3.5 kilo-electron volts emanating from the hearts of galaxy clusters and from the Andromeda galaxy. This signal, while still unconfirmed, is exactly what some models of sterile neutrino dark matter predict. As physicist Dr. Kevork Abazagian explains, these particles would likely have masses measured in kilo-electron volts, placing them squarely in the warm dark matter category. Their slight warmth would give them just enough energy to stream through the early universe, smoothing out the smallest dark matter clumps and potentially resolving the missing satellites problem that troubles the simplest cold dark matter simulations. The hunt for this signal is a painstaking exercise in cosmic forensics. Space-based X-ray telescopes like XMM Newton and Chandra scan the deep sky, collecting photons from the dark, diffuse halos of galaxies, searching for that one specific wavelength of light against an overwhelming background of astrophysical noise. The center of our own Milky Way also shows a faint, ambiguous X-ray excess at this energy, a siren song that could be a discovery or merely a complex astrophysical process we do not yet understand. How do we ever distinguish a true signal from the universe's constant background hum? This search forces us to build ever more sensitive instruments and develop new statistical techniques to tease truth from randomness. The sterile neutrino elegantly bridges the gap between the esoteric needs of particle theorists and the large-scale observations of astronomers, a candidate born from mathematical necessity that might just leave a faint, glowing fingerprint on the cosmos. This slow, meticulous process of elimination and discovery reminds us that the universe reveals its secrets not in shouts, but in whispers, and we must learn to listen with unparalleled patience. A fourth possibility suggests the answer is not a particle at all, but a cosmic fossil. Primordial black holes are theorized to have formed not from dying stars, but in the extreme density of the universe's first second. These ancient remnants could be lurking everywhere, completely dark and invisible, their collective gravity weaving the fabric of the cosmos, the idea championed by physicists like Dr. Bernard Carr was revived by a stunning discovery. When LIGO first detected gravitational waves from merging black holes, the masses involved were unexpectedly heavy, falling into a gap not easily explained by standard stellar collapse. Could these have been primordial black holes formed in the chaos of the beginning, finally revealing themselves through their collisions? Their formation is a story of cosmic extremes. In the violent expansion of inflation, tiny regions of space could have become so overdense that they collapsed directly into black holes. Alternatively, shifts in the fundamental forces during cosmic phase transitions might have created knots of energy dense enough to birth them. These black holes would not be made of anything we recognize as matter. They are pure gravity, frozen knots of space-time from the universe's infancy. Their potential mass range is staggering, from something as light as a small asteroid to heavier than our Sun. If they exist in vast numbers, they could account for some, or even all, of the dark matter. This elegant idea, however, must survive a gauntlet of observational tests. Surveys like EROS and data from the Kepler telescope have diligently searched for these objects by watching for microlensing events. As a primordial black hole passes in front of a distant star, Its gravity acts as a tiny lens, briefly magnifying the star's light. The absence of widespread, frequent lensing rules out primordial black holes, making up all the dark matter across a wide range of masses, particularly those around the mass of a planet. Yet, intriguing windows remain open. For masses much lighter than a planet or in the range of stellar masses, the constraints are weaker, leaving room for these relics to be a significant component. The LIGO mass gap is a tantalizing clue, a hint that the dark matter holding galaxies together might be a population of ancient black holes occasionally merging in the dark. This idea challenges the very definition of matter, proposing that the missing mass is not a substance, but a landscape of gravitational scars from the universe's birth. How often do we find that an old idea, once set aside, finds new life through a fresh perspective? This diversification of the hunt, from waves to particles to primordial fossils, reveals a scientific process rich with imagination, where every possible path must be explored. Deep beneath the mountains of Italy and the Black Hills of South Dakota, humanity listens for a ghost. These are the quietest places on Earth, laboratories buried under a kilometer of solid rock, shielded from the constant rain of cosmic radiation that bombards the surface. Within these silent caverns, scientists have built the most sensitive ears in history, not for sound, but for the faintest tick of a collision. At the heart of the Xeno-NNT experiment, for instance, rests a gleaming vat of ultra-pure liquid xenon, chilled to -100 degrees Celsius. If a dark matter particle, like a WIMP, were to drift through this tank and ever so gently bump into the nucleus of a xenon atom, the impact would create a two-part signal. First, a fleeting flash of light would be captured by an array of sensitive photomultiplier tubes lining the top and bottom of the vessel. Then, a faint electrical charge would drift upward, creating a second signal. This dual signature, the scintillation light and the ionization charge, is recorded in 3 dimensions by a time projection chamber, allowing physicists to pinpoint the exact location and energy of the event within the liquid. The entire apparatus is designed to distinguish this whisper from the background noise of the universe. The greatest challenge is weeding out false signals. A stray neutron, for example, can mimic a dark matter collision. To combat this, detectors are encased in layers of shielding and immersed in immense tanks of purified water, creating a fortress against interference. Scientists like Dr. Laura Bordes have dedicated their careers to this painstaking work, pushing the sensitivity of these instruments to levels once thought impossible. They are testing specific interaction cross-sections, a measure of how likely a dark matter particle is to interact with normal matter. So far, the result is a profound silence. No confirmed detection has been made, yet this very absence is a form of progress, systematically ruling out vast territories of possible particle properties and guiding the theory. Other experiments take a different tactical approach. The Dharma/Libra project, also nestled deep underground in Italy, has reported a curious rhythmic signal for over 2 decades. Its data shows a tiny oscillation that peaks in June and dips in December, matching the rhythm of Earth's journey around the Sun. As our planet moves through the Milky Way's dark matter halo, its orbital motion should create a wind, making the halo seem denser in one direction during summer and thinner in winter. This annual modulation is exactly what Dharma claims to see, yet no other experiment has been able to reproduce this result, creating one of the most enduring and controversial puzzles in modern physics. It is a testament to the monumental challenge of this search. Researchers are essentially waiting for a single, perfect grain of sand to drop in a vast, silent desert, and they must be ready to recognize its fall. This requires years, sometimes decades, of patient observation and relentless refinement of technology. It is a hunt defined by its silence, a search for a shadow by watching for the light it never extinguishes. While our deepest laboratories listen in vain for a direct collision, the entire sky above us might be screaming with evidence. This is the promise of indirect detection, a method that turns our most powerful telescopes into hunters of dark matter's fallout. Instead of waiting for a ghost to bump into us, we scan the heavens for the faint, glowing aftermath of dark matter particles meeting their end. In the dense, dark matter-rich core of our own galaxy, or within the pristine quiet of faint dwarf galaxies, these invisible particles could occasionally annihilate upon contact, transforming their mass into a flash of familiar particles we can actually see. Or they could be slowly decaying over billions of years, emitting a steady drizzle of radiation. Our space telescopes, like the Fermi Large Area Telescope, constantly sweep the sky, mapping the universe in high-energy gamma rays. They are looking for an unexplained glow, an excess of light that cannot be accounted for by any known celestial object. One of the most tantalizing clues is the galactic center GV excess, a mysterious surplus of gamma rays emanating from the heart of the Milky Way. For a time, this seemed like a perfect signature of dark matter annihilation. Physicist Dr. Tracy Slatire, who has done pioneering work on such signals, points out that the challenge is immense. The galactic center is a crowded, chaotic place, blazing with pulsars and other extreme astrophysical objects that also produce gamma rays. Disentangling a potential dark matter signal from this stellar cacophony is like trying to hear a single voice in a roaring stadium. The debate over this excess showcases the intricate dance between observation and theory, where a promising signal must survive the gauntlet of alternative explanations. Another promising channel is the search for a perfect line. When two dark matter particles annihilate, they could, in theory, produce two gamma rays of identical specific energy. This would create a sharp, unmistakable spike in the data, a spectral fingerprint that would be very difficult for conventional astrophysics to mimic. While such a definitive line remains elusive, other messengers offer clues. The Alpha Magnetic Spectrometer, a MS-02, mounted on the International Space Station, has measured a curious abundance of positrons, the antimatter counterparts to electrons in cosmic rays. This positron excess could be the product of distant dark matter decay, though here too, more mundane sources like pulsars are strong contenders. To find a cleaner signal, astronomers often turn to dwarf spheroidal galaxies. These are ancient, faint satellites of the Milky Way that are believed to be overwhelmingly dominated by dark matter, with very few of the conventional astrophysical sources that create background noise. A dwarf galaxy like Reticulum 2 has drawn intense scrutiny because observations have revealed it to be unexpectedly bright in gamma rays. Is this the long-sought proof of dark matter annihilation within its pristine halo, or is it an unusual cluster of pulsars? The interpretation remains hotly debated. This is the fundamental challenge of indirect detection. How do we decode the universe's signals when multiple compelling explanations coexist? Every anomalous flicker of light must be weighed against the possibility of a new type of star or a previously unknown cosmic accelerator. It forces a collaboration between particle physicists who predict the signals and astronomers who understand the complex foregrounds of the sky. This method truly turns the cosmos into a vast natural laboratory, where the search for the invisible is conducted by meticulously studying the light it might, just might, leave behind. Our search for the invisible now turns to the most violent environments we can create. Beneath the border of France and Switzerland, the Large Hadron Collider smashes protons together at velocities infinitesimally close to the speed of light. Within these collisions, for a fleeting fraction of a second, energies not seen since the universe's first moments are unleashed. It is in this primordial fire that we hope to forge the very substance that evades us. These experiments do not look for dark matter directly. Instead, they search for its ghostly signature in the debris. When two protons annihilate, their energy must be accounted for. If a new, invisible particle is created in the blast, it would carry away a portion of that energy without leaving a trace in the surrounding detectors. This missing energy, specifically an imbalance in the momentum measured perpendicular to the beamline, is the telltale clue known as missing transverse energy. Think of it like a cosmic crime scene where the bullet is found, but there is no shooter. The energy is gone, and the only explanation is that something we cannot see has taken it. This is the principle behind searches for events with a single, powerful jet of particles or a single high-energy photon recoiling against nothing, phenomena known as monojet and monophoton signatures. It appears as if a visible particle was kicked by an invisible one, a cosmic billiard shot where we only see one ball move, leading theorists like Dr. Nima Arconi Haim suggests these collisions could be our gateway to an entire dark sector, a hidden universe of particles that interact with our own only through the faintest of links, perhaps via a mediator particle that acts as a bridge between the familiar and the unknown. The monumental experiments ATLAS and CMS are constantly analyzing these collisions, setting ever more stringent limits on how dark matter might couple to the standard model. For instance, if dark matter is connected to the Higgs boson, the collider might produce it alongside a Higgs, leaving a signature of a Higgs decay with missing energy. So far, no definitive signal has emerged. This relentless null result is itself a profound guide, systematically closing doors and forcing theoretical models to become more refined and creative. There is a deep irony in this method. To find the cold, dark relics that sculpt the cosmos, we must generate temperatures trillions of times hotter than the heart of the sun. We are essentially creating miniature Big Bangs, pushing our technology to its absolute limits to glimpse a particle that, by its very nature, wishes to remain hidden. This collider search forms the third pillar of our experimental triad, complementing the quiet listening of direct detection and the cosmic forensics of indirect searches. Together, they weave a net around the mystery, hoping that somewhere in the silent depths of a mine, in the faint light of a distant galaxy, or in the fiery aftermath of a particle collision, the shadow will finally step into the light. Our own galaxy holds clues to the invisible ocean it swims within. Subtle gravitational tugs on stars and the faint heating of ancient stellar corpses offer a fourth way to probe the dark, using the cosmos itself as our laboratory. When dark matter particles drift through a dense object like a neutron star, they can be gravitationally captured, sinking to its incredibly dense core. There they may annihilate, releasing energy that gently warms the ancient star. For an old, cold neutron star, this unexpected warmth could be the only sign of an invisible interaction. Astrophysicist Dr. Rebecca Lean studies how these cosmic lighthouses could reveal asymmetric dark matter, a model where the particle is its own antimatter counterpart, leading to efficient annihilation and a detectable thermal signature. This method turns entire stars into vast, natural particle detectors. We can also watch the delicate dance of wide binary stars, pairs separated by vast distances. Their orbits are so fragile that the gravitational friction from a diffuse cloud of dark matter, a local halo substructure, could subtly alter their paths over time. The European Space Agency's Gaia mission is revolutionizing this search, providing exquisitely precise positions and motions for over 1 billion stars. This data lets us measure the Milky Way's disk heating, a process where passing dark matter clumps like underwater reefs gravitationally perturb stellar orbits, stirring up the galactic plane over billions of years. It even allows us to study the resonance of the Milky Way's central bar, a vast structure of stars whose rotation may be influenced by the specific distribution of the dark matter halo enveloping it. Some researchers have even proposed that the strange orbital clustering of distant solar system objects, a puzzle that led to the hypothetical Planet 9, could instead be explained by a concentrated clump of dark matter. While highly speculative, this idea highlights how astronomical anomalies force us to consider every possible explanation, blurring the line between established theory and creative, testable conjecture. How often does a mystery in one field of science illuminate a completely different frontier? These astrophysical probes are a testament to ingenuity, a way to conduct multi-million-year experiments for the price of telescope time and human curiosity. They remind us that when our machines are not enough, we can learn to read the whispers of the stars themselves, searching for the subtle imprint of the dark on the world of light. Deep within a South Dakota gold mine, a cylinder of liquid xenon waits in the dark. The LUX Zeppelin experiment, or LZ, is a silent sentinel, representing the next evolutionary leap in our direct hunt for the invisible. Its core is a 10-ton vat of ultra-pure xenon, a volume so vast it dramatically increases the odds that a wandering dark matter particle might finally leave a trace. This is not merely a bigger version of its predecessors, it is a fortress against interference, engineered to hear a whisper in a cosmic hurricane. The entire apparatus is submerged within a titanic tank of purified water, itself nestled in a clean room excavated from the ancient rock, all to shield it from the natural radioactivity that constantly bombards our world. Dr. Hugh Lippincott, a project lead, explains that LZ is designed to probe WIMP interactions at a level of sensitivity we have never before achieved. It aims to measure the cross-section, the probability of a collision, down to a vanishingly small number, a realm where a new background noise emerges, the neutrino fog. This fog is created by the countless neutrinos streaming from the Sun and other cosmic sources, particles so ghostly they were once thought undetectable. Now they represent the final frontier of background, the point at which even the most perfect dark matter signal would be drowned out by nature's own chatter. To peer through this fog, LZ employs a dual-phase time projection chamber. If a particle interacts within the liquid xenon, it creates a flash of light and knocks electrons loose. Those electrons are then pulled upward by a powerful electric field into a thin layer of xenon gas, where they produce a second distinct flash of light. By comparing the timing and strength of these two signals in three-dimensional space, physicists can pinpoint the exact location and energy of the event, and crucially, determine whether it was likely caused by a heavy WIMP or a lighter background particle. The stakes could not be higher. A clear signal from LZ would be a monumental discovery, the culmination of a decades-long quest, but a definitive null result, finding nothing at all, would be equally profound. It would force us to close the book on a wide range of possible WIMP properties, compelling theorists to abandon cherished models and venture into more exotic territory, perhaps toward lighter dark matter or actions. This is the iterative heartbeat of science, where every answer, even a silent one, reshapes the path forward. The immense effort behind LZ, a collaboration of hundreds of scientists across the globe, is a testament to our determination to solve this mystery. It embodies the principle that we must exhaust every possibility here on Earth before we can truly understand what whispers to us from the stars. Yet another instrument of discovery waits in the wings, a space telescope named Athena, poised for a launch in the 2030s. Its mission is to stare into the hearts of galaxy clusters, not to see the light of stars, but to map the searing heat of the million-degree gas that fills the space between them. This hot gas is a fossil record of the cluster's violent formation, and its intricate structure is sculpted by the gravitational pull of the invisible dark matter halo. Athena's powerful spectrometers, particularly the X-ray integral field unit, will dissect the light from this gas with a precision never before achieved. It will measure slight shifts in the energy of X-rays, revealing the turbulent motions and deep gravitational wells of these colossal structures, allowing scientists to weigh the dark matter directly. But its most tantalizing goal is to hunt for a ghostly fingerprint. That unexplained X-ray line at 3.5 kilo-electron volts, spotted flickering in the cores of clusters and galaxies, could be the decay signal of sterile neutrino dark matter. Athena will have the spectral resolution to settle the debate once and for all. Is this faint glow the final sigh of a decaying dark matter particle, or is it merely the collective emission of mundane astrophysical sources like hot potassium ions? Dr. Kirpal Nandra explains that by staring for long, deep exposures at relatively quiet clusters like Virgo, where the background noise is lower, Athena could potentially isolate a true dark matter signal from the cosmic static. This represents the immense patience of astronomy, a field where a question asked today might be answered by a machine launched into space a decade from now. How do we maintain the thread of curiosity across generations of scientists, linking our current puzzles to the revelations of a future we can only imagine? Athena is not just a telescope, it is a promise to the future, a vessel for questions we are only now learning how to ask. While our largest telescopes scan the heavens and our deepest laboratories listen in silence, another frontier of discovery is being prepared in the most extreme environments on Earth. The next generation cosmic microwave background experiment, known as CMBS-4, will deploy a powerful array of telescopes at the South Pole and in the high Chilean Andes. Its mission is to read the oldest story in the universe, the cosmic microwave background, with a precision that borders on the impossible. It will map the faint temperature variations and subtle polarization of this ancient light in microscopic detail, searching for the faintest imprints left by dark matter on the infant cosmos. This is not merely a sharper image, it is a deeper reading of a cosmic text, looking for scribbles in the margin left by the invisible hand that shaped everything. Dr. John Karlstrom, a leader in this field, explains that CMBS-4 could distinguish between competing dark matter models by measuring incredibly small-scale distortions. The heat and light from dark matter annihilation or decay in the early universe would have left a unique scar on the formation of the first atoms, a faint echo that these ultra-sensitive bolometers are designed to capture. The experiment will also hunt for signs of cosmic birefringence, a twisting of the light's polarization that could be caused by dark matter interacting with photons in a way we have never seen. Even the mass of neutrinos, the lightest known particles, is tied to this puzzle, as their properties affect how the cosmic web forms under the dominant influence of dark matter. Every new data point acts as a key, locking some theoretical doors while opening others. For instance, if CMBS-4 finds definitive evidence for dark matter photon scattering, it would instantly revolutionize our understanding of its particle properties, transforming it from a purely gravitational entity to one that can touch light itself. This immense project stands on the shoulders of pioneers like the Planck satellite, weaving a cumulative tapestry of knowledge where each thread strengthens the whole. The goal is a final, precise measurement of the dark matter parameters that have guided the universe since its first moments, pushing cosmological precision to its absolute limit. This is the power of legacy science, a patient, generational effort to read the universe's opening chapter not for the story we expect, but for the one it has been waiting to tell. The scale of this ambition is almost beyond comprehension. Imagine a detector containing 40 tons of liquid xenon, a volume so immense it represents the ultimate expression of our direct search for the invisible. This is the proposed Darwin Observatory, a machine designed not just to find dark matter, but to hunt for it until the laws of physics themselves say we can go no further. Its staggering size is the key to its ultimate sensitivity. With a target mass that dwarfs current experiments, Darwin would be able to probe for incredibly faint and rare interactions, from the lightest theoretical dark matter particles to elusive actions. Dr. Mark Schumann, a collaborator on the project, explains that its goal is to achieve a state of background-free operation. In such a pristine environment, any signal that emerges would not be a mere hint, but a statistically undeniable event, a potential conclusion to a century-long mystery. The path to this goal is paved with monumental engineering challenges. The entire system must be shielded from the faintest traces of natural radioactivity, even from radon gas that seeps from the surrounding rock. Purifying 40 tons of xenon to an unimaginable level of purity, and scaling up the delicate systems that read its whispers of light and charge, is a feat of human ingenuity in itself. But the reward for this effort is a tool of unparalleled versatility. Darwin would cast a wide net, capable of searching for various types of particle interactions far beyond the classic WIMP model. It would even listen for the gentle rain of solar neutrinos, particles that will eventually create an irreducible background noise known as the neutrino floor. At that profound threshold, the faint kicks from these known cosmic ghosts would perfectly mimic the signal we are searching for, testing the absolute limit of what direct detection can ever teach us. This is the final frontier of the empirical quest, to build a machine so exquisitely sensitive that it begins to hear the constant, quiet hum of the universe itself, and within that hum, to listen for the one note that has never been played. What does it mean to push an investigation to the very edge of what is possible, where the signal and the background become one and the same? The confirmation of dark matter would tear a new chapter into the very rulebook of physics, forcing a revision of the standard model that has guided our understanding for decades. This discovery would be far more than just adding a new particle to the list. It would be the key that finally unlocks the door to a deeper reality. For generations, physicists have struggled to unite the two great pillars of modern science, the quantum world of the tiny and the gravitational cosmos of the immense. Dark matter, a substance that clearly exerts gravity but remains invisible to all other forces, might be the bridge that connects them. Its existence strongly hints at a vast, hidden dark sector of the universe, a complete shadow realm with its own particles and forces, interacting with our familiar world only through the faintest gravitational whisper. Theoretical physicist Dr. Sabine Hossenfelder explores this possibility, suggesting that such a dark sector could possess a complexity that mirrors our own, with the potential for dark atoms, dark molecules, and even dark chemistry playing out in parallel to everything we see. This would fundamentally reshape our cosmic understanding, revealing that the universe we observe is just a small, luminous island in a much larger, darker ocean. The implications ripple back to the very beginning of time. Dark matter's gravitational pull was likely the essential anchor that allowed the universe to grow from the smooth soup of the Big Bang into the intricate cosmic web we see today. Its properties might have even guided the period of cosmic inflation that moment of fantastically rapid expansion that set the initial conditions for everything. Some theories suggest that the nature of dark matter could be tied to the existence of a multiverse, with its specific characteristics being a random outcome in our particular cosmic bubble. This substance could even influence fundamental concepts like the arrow of time and the flow of entropy, acting as the hidden background against which the drama of our visible universe unfolds. Throughout history, our perception of reality has been shattered and rebuilt by such discoveries. The Copernican revolution displaced us from the center of the universe. Einstein's relativity warped our concepts of space and time. The confirmation of dark matter would be the next great paradigm shift, a humbling reminder that the vast majority of cosmic reality is written in a language we are only just beginning to learn. This search is driven by a fundamental human curiosity, a need to understand the hidden architecture of existence, and it pushes us to look beyond our current frameworks toward answers we cannot yet imagine. The life story of a galaxy is written in the gravitational pull of the unseen. From a formless primordial cloud, a majestic spiral emerges, its graceful arms tracing the contours of an invisible hand. Dark matter provides the essential stability, the cosmic bedrock upon which luminous structures can slowly build. Its vast, spherical halos act as deep gravitational wells, capturing vast reservoirs of hydrogen gas and cosmic dust. Without this anchoring presence, the first clumps of normal matter would simply drift apart, their potential for star formation lost to the void. Dr. Sandra Faber explains that the stable disk of a galaxy like our own, a prerequisite for the orderly orbits of stars and planetary systems, is a direct gift from this dark foundation. It is this stability that allows supermassive black holes to form and sustain at galactic centers, which in turn regulate a galaxy's activity and potentially influence its habitability. The intricate dance of creation is choreographed by gravity we cannot see. In the virtual universe of supercomputer simulations like Illustris, we can watch this cosmic drama unfold. The code begins with the faint ripples of the early universe and lets physics run its course. When dark matter is included, the result is breathtakingly familiar. Vast halos coalesce first, their immense gravity pulling in streams of ordinary matter. This gas cools, condenses, and eventually ignites into the first stars, painting the dark scaffolding with light. The simulation accurately reproduces the full diversity of galaxies we observe, from elegant spirals to featureless ellipticals. The morphology of a galaxy, its very shape and structure, is not random. It is largely determined by the properties of its dark matter halo. A slowly rotating halo with ample gas may give rise to a grand spiral, while the violent merger of halos can stir up the stellar population, erasing the disk to form a smooth, elliptical galaxy. These galactic collisions are the ultimate testament to dark matter's dominant role. When two galaxies meet, it is primarily their dark matter halos that interact first, their gravity dictating the entire encounter. The visible stars, separated by vast distances, often pass by each other without a single stellar collision, but the dark matter halos, extended and massive, engage in a gravitational tug of war. They can strip material from one another, trigger immense waves of new star formation, or ultimately merge into a single, larger halo. We are on a direct course for such an event. In several billion years, our Milky Way and the Andromeda Galaxy will begin their slow, inevitable merger. The outcome of this cosmic dance will be orchestrated not by the stars we see, but by the dark matter halos that surround them. They will determine whether a new, larger spiral forms, or if the result is a giant elliptical galaxy, its stellar orbits randomized by the invisible gravitational turmoil. Even within a single galaxy, dark matter influences the rhythm of star birth through complex feedback mechanisms. When massive stars explode as supernova, they blow powerful winds that can heat surrounding gas and even eject it from the galaxy. This process self-regulates star formation, preventing a galaxy from burning through its fuel too quickly. Yet this feedback operates within the gravitational confines of the dark matter halo. A massive halo can retain this heated gas, allowing it to eventually cool and fall back to fuel future generations of stars. A weaker halo might lose its gas forever, quenching star formation and leaving the galaxy to fade. This intricate interplay between the visible and the invisible shapes the life cycle of every galaxy. How does an unseen framework sculpt the celestial beauty we observe on a clear night? The spiral arms of a distant galaxy are not just a pattern of light, they are a gravitational signature, a shadow play cast by the dominant, dark essence of the cosmos. The same gravitational pull that sculpted galaxies now fights a losing battle for the cosmos itself. Dark matter provides the cosmic backbone, the weight that slows the universe's expansion, but it is locked in a fundamental struggle with a phantom force, dark energy. The fate of everything hinges on the balance between this invisible anchor and this mysterious push. The universe's geometry and ultimate destiny are dictated by its total density, a critical value where dark matter is a dominant contributor. Current measurements show dark energy is winning, driving an accelerated expansion that will eventually overwhelm gravity's pull. Cosmologist Dr. Katie Mack describes a future where this expansion stretches the cosmic web to its breaking point. Over trillions of years, the vast filaments of dark matter that connect galaxy clusters will be severed. Galaxies will become isolated island universes, their dark matter halos the only things preventing their own stars from being stripped away into the deepening void. We can trace this cosmic fate through several profound scenarios. In a big freeze, the expansion continues indefinitely, with dark matter ensuring galaxies remain bound even as they recede from one another into cold, dark isolation. Stars will burn out and space itself will approach absolute zero. A more violent end is the Big Rip, where the acceleration becomes so intense that it tears apart first galaxy clusters, then galaxies, solar systems, planets, and finally the very fabric of spacetime. Dark matter's distribution influences the timing and possibility of this cataclysm. Its gravitational glue the last thing to be overcome. The properties of dark matter itself could subtly alter this timeline. If dark matter particles were to slowly decay into radiation over eons, this would gradually reduce the gravitational anchor holding cosmic structures together. This decay would slow the growth of new galaxies and accelerate the dissolution of the old, influencing the universe's long-term entropy production. The entire cosmos would slide toward equilibrium, a featureless state of maximum disorder, more quickly. Even more speculative is the potential link to vacuum decay, where a dark matter interaction could theoretically trigger a catastrophic phase transition in the fabric of reality, rewriting the laws of physics in a propagating bubble at the speed of light. These are not just stories about an impossibly distant future. They are the logical extensions of the physics we are trying to understand today. Our search for the nature of dark matter is inextricably linked to the universe's birth and its ultimate death. It is a humbling perspective that connects the most local mystery, the ghost in our laboratories, to the grandest possible timeline. This invisible substance is not merely holding galaxies together. It is one of the two fundamental architects of cosmic destiny. Its silent tug of war with dark energy writing the final chapter for all of reality. The hunt for the invisible is quietly revolutionizing our own world. Those exquisitely sensitive dark matter detectors, built to hear a whisper in a cosmic storm, are now finding extraordinary uses here on Earth. The same technology that shields a vat of xenon from background radiation can be adapted to create incredibly pure materials for medical implants. The cryogenic systems that cool detectors to near absolute zero are pushing the boundaries of quantum computing. This is the hidden dividend of fundamental research, where a question about the cosmos sparks a cascade of innovation. Physicist Dr. Juan Coller points to experiments like Coherent, which was designed to detect a faint neutrino signal. In the process, it pioneered new methods of neutron detection that are now being applied to safeguard nuclear materials and to improve the precision of particle beam therapy for cancer. The connection is not a coincidence but a pattern. The relentless drive to eliminate all background noise to sense the most elusive events forces engineers to solve problems nobody knew existed. These solutions then ripple out into other fields. Take the silicon photomultiplier, a device born from the needs of astroparticle physics. This incredibly sensitive light sensor, capable of detecting single photons, is now a key component in next-generation positron emission tomography, or PET, scanners. This means doctors can image the inner workings of the human body with greater clarity and lower doses of radiation, leading to earlier diagnosis and better outcomes for patients. The algorithms developed to sift through terabytes of data from cosmic observations are now helping geologists map mineral deposits and archaeologists peer inside ancient structures without disturbing them. International collaborations, essential for funding and staffing these vast projects, become engines of technology transfer, with knowledge and techniques flowing across borders and disciplines. This practical legacy reminds us that the value of reaching for the stars is often measured in the tools we create along the way. Our curiosity about the universe's greatest mystery is gifting us with a deeper understanding of our own world, from the human body to the ground beneath our feet. The immense scale of dark matter research inevitably raises a profound ethical question. Billions of dollars and decades of human effort are poured into instruments that listen for ghosts, into telescopes that map the invisible. In a world facing immediate challenges like health crises and environmental shifts, how do we justify such a monumental investment in fundamental knowledge? This is not a new dilemma, but it is sharpened by the sheer ambition of projects like the next-generation Cosmic Microwave Background Observatory or the proposed 40-ton Darwin detector. These endeavors require global cooperation and funding on a scale typically reserved for national priorities, sparking a necessary debate about the allocation of our collective resources. Philosopher Dr. Neil Levy suggests that the value of such curiosity-driven science is intrinsic. It is a fundamental expression of our humanity to seek understanding, a pursuit that historically fosters unexpected innovation and builds bridges between nations that might otherwise struggle to find common ground. Critics, however, rightly emphasize the opportunity cost. The funds and brilliant minds dedicated to solving a cosmic mystery could be directed toward developing cleaner energy sources, improving food security, or advancing medical care. This moral calculus forces us to weigh the long-term quest for cosmic meaning against the urgency of present-day human need, yet the division is rarely so clear. The technological fallout from this research already ripples into our daily lives. The same cryogenics that cool dark matter detectors are advancing quantum computing. The ultra-pure materials developed to shield against background radiation are finding uses in medical implants and sensors. The armies of scientists and engineers trained to build these experiments form a highly skilled workforce that disperses into other critical fields, from data science to materials engineering. The Apollo program, often cited in this debate, did not just land humans on the moon. It inspired a generation to study science and engineering, and its technological legacy permeates modern medicine, computing, and consumer electronics. Similarly, the relentless drive to sense the invisible could one day yield hypersensitive environmental monitors capable of tracking pollution at a molecular level or new ways to manage nuclear materials. This does not erase the ethical tension, but it reframes it. The choice is not purely between knowledge and welfare. It is about investing in a pipeline of discovery whose ultimate practical benefits are unpredictable but often transformative. The journey to comprehend the dark universe is also a journey that equips us with new tools to understand and improve our own world, weaving a subtle thread between the stars above and the ground beneath our feet. Another layer of ethical consideration emerges not from the cost of knowledge, but from its potential power. The same fundamental understanding that reveals the cosmos could one day grant us the ability to interact with its hidden forces. Envision a distant future where humanity has learned not just to detect dark matter, but to manipulate its distribution. We might conceive of dark matter engines, using concentrated halos to warp space-time for propulsion or to generate vast energy. Such a technology would rewrite the rules of civilization, offering journeys across the galaxy. Yet, tampering with the universe's gravitational skeleton carries profound, unforeseeable risks. Altering the dark matter scaffold in a region of space could theoretically disrupt the delicate orbital dance of stars within a galaxy, or create unstable configurations of matter with exotic properties. The theoretical risk of initiating a cascade, where a manipulated patch of dark matter influences space-time in unexpected ways, cannot be entirely dismissed, even if it remains a speculative concern far beyond our current grasp. Philosopher Dr. Nick Bostrom, who studies existential risks, notes that any powerful new physics carries a dual-use potential. The same principles that could power a starship might, under different conditions, be directed in ways that pose hazards. While dark matter's incredibly weak interactions make such scenarios highly unlikely for centuries, the very possibility invites deep reflection. How would international treaties adapt to govern a technology that controls gravity itself? The precedent set by nuclear non-proliferation and outer space agreements suggests a framework, but regulating a force that permeates every corner of the universe presents an unprecedented challenge. This is where the precautionary principle in science becomes vital, advocating for careful peer review, transparency, and gradual testing to mitigate risks long before any application becomes feasible. Our responsibility as a species grows with our understanding. The drive to explore the darkest secrets of the cosmos must be matched by a parallel commitment to ethical foresight, ensuring that our curiosity illuminates the future rather than casting a new, unintended shadow. How do we balance the human imperative to reach for the stars with the profound duty to protect the cosmic order we are only beginning to perceive? Our universe might be a grand illusion, a cosmic stage where the actors we see are outnumbered by invisible stagehands. For centuries, science has relied on a simple premise that we can understand reality through observation. Yet dark matter shatters this foundation, presenting a cosmos where the dominant form of matter reveals itself only through its ghostly gravitational pull. We are like the prisoners in Plato's allegory of the cave, mistaking the shadows on the wall for the entirety of existence, unaware of the profound realities casting those shadows just beyond our sight. This forces a deep philosophical rift. Do we trust only what we can directly measure, or do we accept the existence of entities whose nature we deduce from their undeniable effects on the world we can see? Philosopher Dr. Tim Maudlin frames this as the conflict between scientific realism and instrumentalism. A realist argues that dark matter is a real, physical substance, even if we cannot yet touch it, because its explanatory power is overwhelming. It is the only way to make sense of the spinning galaxies, the bent light, and the cosmic blueprint. An instrumentalist, however, might see dark matter as merely a useful conceptual tool, a mathematical placeholder that helps our equations work without committing to its physical reality. This is not an abstract debate. It echoes throughout the history of science. The atom was once a philosophical concept, an unseeable unit invoked to explain chemical reactions. For generations, it was a theoretical construct until technology advanced and we could finally image individual atoms, transforming a useful model into a tangible truth. Black holes suffered a similar journey, existing for decades as a bizarre mathematical consequence of Einstein's equations before we gathered observational proof of their reality. In each case, the unobservable became observable. Our current search for dark matter is a modern iteration of this ancient process. We are building the tools to step out of the cave, to turn our faces from the shadows toward the source. The bacteria teeming in a drop of water were once an invisible world, completely unknown and unimaginable to anyone without a microscope. Today, we accept their reality without question. Dark matter may be our next great unveiling, waiting for the right technological lens to bring it into focus. This journey challenges our deepest assumptions about knowledge itself. How do we know what is real? Is reality limited to what our biological senses or current instruments can detect? Or does it extend into a vast, unseen landscape that we can only map through the subtle traces it leaves on the visible world? The existence of dark matter suggests that what we perceive is only a tiny fraction of what actually exists, a humbling reminder that our cosmic home is far stranger and more wonderful than it appears. Our planet drifts in an unseen ocean. Every breath you take, every mountain you see, is immersed in a sea of dark matter, a substance that defines the cosmos yet remains utterly alien to our senses. This simple fact delivers a profound blow to our human-centered view of the universe. We have long considered ourselves the pinnacle of a cosmic order built from the atoms of the periodic table. Yet dark matter reveals this familiar matter, the very stuff of our bodies and our world, to be a cosmic afterthought, a mere 5% of the universal budget. The overwhelming dominance of this invisible substance forces a humbling perspective shift. We are not the main characters in a universe designed for us. We are a rare and delicate exception, a flicker of light in a reality dominated by shadow. The late astronomer Carl Sagan's reflection on our pale blue dot gains a deeper, more unsettling dimension when we realize that the vast majority of cosmic mass is not just distant, but fundamentally other. It is a form of matter that does not reflect, emit, or absorb light. It does not form the planets and stars we recognize. It is a ghost in the machinery of the cosmos, and we are living on one of its few material ornaments. This challenges the very core of human exceptionalism. We are like fish who have only just become aware of the water they have been swimming in all along, a medium that is essential to their world but completely invisible to their immediate senses. Our entire existence, it turns out, is dependent on this hidden framework. The dark matter halos that cradle galaxies provided the gravitational wells for the first stars to ignite. Without this invisible anchor, the cosmic gas would never have collapsed into the structures that eventually led to our solar system and our planet. The iron in your blood and the calcium in your bones were forged in stellar furnaces that could only have formed within the stable cradle of a dark matter halo. This interconnectedness is staggering. We are not just living in a universe with dark matter. We are here because of it. Our existence is a direct consequence of this vast, unseen architecture. This realization can reshape philosophical perspectives on meaning. For some, it underscores a universe indifferent to human concerns, a cold, dark ocean where life is a fleeting accident. For others, it inspires a sense of profound wonder and unity. The same mysterious substance that holds the galaxies together also binds us to the deepest workings of the cosmos. Our quest to understand it becomes a shared human endeavor, a puzzle that transcends national borders and cultural differences. In laboratories across the globe, from deep underground to the peaks of mountains, we are united by this single, magnificent mystery. This shared pursuit of knowledge, this collective reach into the dark, may be one of the most meaningful legacies of our species. It reminds us that our true place in the cosmos is not as its masters, but as its students, humbled by the darkness and driven by a fundamental need to bring it into the light.